Hi. As discussed as the start of our module on radiation detection, detection is based on first, ionization in the gas, second, excitation in certain solids, and also in chemical and nuclear reactions in the materials, third. The ionization in gas for detection was described in part 2 of this module, the discussion on gas field detectors. And this time, we will learn detection based on excitation or ionization in certain solid state materials. The part 3 of our module on radiation detection will discuss solid-state detectors. Although generally when they say solid-state detectors, they refer to semiconductor detectors. In this module, we set this at the second type of detector, and types of which are semiconductors, scintillation detectors, and luminescence detectors. Okay, so let's start by looking at the diagrams in solid-state physics. This basically shows us the location of electrons in a material. The dashed lines in the region represents the occupied and valence band where electrons are bound and not free to move. Electrons usually exist in this region. The white region at the top represents the conduction band where electrons can move freely. And then at room temperature, thermal agitation cannot promote electrons to the conduction band because the separation energy is about 10 electron volts. These materials are called insulators, examples of which are glass, plastic, rubbers, and so on. Now, there are some materials wherein the valence and conduction band overlap, like this one, wherein the electrons can move freely from the valence band to the conduction band and back. These materials are good conductors of electricity, like metals. Call them conductors. Then, there are also materials where the separation distance of these bands are within 1 electron volt. Thermal energies can promote electrons to the conduction band easily, but may also fall back to the valence band quickly and jump back and forth to the valence and conduction band. This region is somewhat partially filled with electron and holes, thus is considered a neutral region. Then we can use this region to be used as a radiation detector, as a solid detector, as solid state detector, as we say. So solid state detectors refers to types of detectors with crystalline substances that exhibit measurable effects when exposed to radiation. Electrons normally exist in the valence band, and ionizing radiation may rise the electron from the valence band to the exciton or conduction band. The vacancy left by the electron is known as the hole. So this is the electron from the conduction band and left a hole which is positively charged. So if you put a cooling system in this region, the conduction band will be empty because there are no thermal energies that can promote the electrons from the valence band to the conduction band. So in this figure, you have the electrons here, the negative charged, and the positive charged, or the holes, on the top region. When radiation strikes this region, electrons will be excited the conduction band, and the applied voltage will sweep the electrons, and proper electronics collects the pulse. Semiconductor detectors are also called solid-state ionization chambers because they operate like ionization chambers. Just the difference is that charge carriers are not electron hole pairs or electron ion pairs like in gas fields, but we call them electron hole pairs. So let us look closer to the PN junction diode. This PN junction diode is connected in reverse bias. In here, we have an N-type semiconductor, which means that the majority are electrons. Majority carriers are electrons, and a p-type semiconductor, which is doped with more holes. There is a depletion region between this p-n junction diode wherein electrons combine with holes, thus making the region neutral. The reverse bias applied to it has a low current that goes along this circuit, and that in this region there will be motions of holes and motions of electrons, but generally considered as a neutral region. Thus, we can utilize this region as our ionization chamber. So what we can do is when an alpha particle enters this depletion region, electrons are excited to the conduction band, leaving a hole in the valence band and producing what we call the electron hole pairs. The transfer of energy to the electron produces electron hole pairs with ionization potential of approximately 3 electron volts. So if we have, since the energy of alpha particles ranges from 3 to 6 mega electron volts, and the band gap of this semiconductor is about 3 electron volts, then there will be millions of electron hole pairs produced in this semiconductor detector. And this will lead to the movement of electrons to the circuit and measured as a current pulse. So the sensitivity of solid-state detectors is about 10 to the 4 times higher than that of gas-field detectors due to this lower ionization potential. So these are the types of semiconductors. We have this as HPG, or high purity germanium detector, on top of a liquid nitrogen dewar. So this type of detector has excellent energy resolution, and this is actually the gold standard for gamma spectrometry. Main applications of semiconductors are in spectrometry for gamma and alpha particles. And for low energy radiation, we use the silicon lithium diode, which also requires cooling. And for room temperature detectors, we have cadmium telluride. Apart from spectrometry, this type of detectors can also be used for dose and dose rate measurements. Next, we have another type of semiconductor or solid-state detector. We call it the scintillation detectors. This is schematic diagram of our sodium iodide, wherein we have 3 regions. We have scintillation region, where the scintillation process occurs. We have the conversion of light, which is here in the photocathode region, and the charge multiplication, which happens in this photomultiplier tube. So let's look at them one by one. So this scintillation detector, note that the energy of the incident photon is proportional to the pulse height. The first step is the production of the light, or the scintillation process. So the energy of the photon is imparted to the scintillant or the scintillation material via photoelectric, Compton, and pair production. So they have the ionization track, and the electron produced causes excitation or ionization, but allowed to excite, and then with the energy in the UV to visible range. This is what we call the scintillation part. So what does this happen? So when we allow the electrons to excite, from the conduction band to the valence band, there's a possibility that the energy will be absorbed within the scintillation material. So in this part, the sodium iodide, for example, they have called the dopant a thallium dope, wherein it adds an energy band here that allows transition from the conduction band to this exciton band, and further the excitation to the valence band, producing light, producing photons of lower wavelength. Thus, we can be able to see this in the UV visible range. Then, the light produced in the scintillation region is converted into an electron. The visible light passes through the coupling and interacts with the photocathode, converting the light into photoelectron. This is what we call the primary electron formation. So the electrons are guided towards the dynode by the focusing electrode. And then the third stage, we have charge multiplication in the photomultiplier tube. So the low energy electron is accelerated towards the dynodes, producing secondary electrons. The secondary electrons then move to the second dynode, the third, and so on, causing charge multiplication. The collection of charges in the anode then generates the current or pulse that can be measured. These are examples of scintillation detectors. So this is a sodium iodide, and this is a sealed crystal where the scintillation happens. This is a type of scintillation for neutrons with zinc sulfide as a material, and this is a type of contamination meter. So in this type of detector, since charge multiplication is very dependent on the dynode voltage, the detector requires a stable voltage supply. This type of detector is used in gamma spectrometry, but with higher efficiency than high purity germanium but with lower resolution. Scintillation detectors like this can detect alpha, beta, and photon, and sometimes neutron radiation depending on the scintillation material used. And these are widely used for radiation monitoring and dose measurements. So this is a comparison of the HPGE gamma spectrum, wherein we can see here that the resolution of the HPGE detector is way better than the resolution of our sodium iodide detector. Higher resolution means our detector is able to discriminate or to identify two separate instances at two separate measurements clearly. Another type of scintillation detector can use organic materials such as anthracene and steel bean. These are liquid solutions of organic materials. We call them liquid scintillants. And here we have this scintillation material and coupled with a photomultiplier tube. This type of detector is used for measuring beta emissions. Another type of solid-state detector is our luminescence detectors, wherein it uses electron trapping process. So the energy absorbed by the electron from the valence band prompts it to higher energy band, but in a forbidden band. The electrons are trapped when exposed to radiation and are stable at normal temperatures. And if heated or subject to light, the trapped electrons return to valence band and emits light. The intensity of the light emitted measures total accumulated dose. An example of a luminescence detector is this, a thermoluminescent detector, wherein the phosphors absorb energy from ionizing radiation and release light when heated above 100 to 300 degrees Celsius. The intensity of the light under this glow curve will give us the amount of dose absorbed by the material. This type of detector can detect beta particles, gamma, and neutrons depending on our scintillation luminescence material. So the intensity of the light measured is related to the radiation dose. Examples of materials for gamma measurements or for gamma detection are calcium sulfate or fluoride, and for neutrons, lithium fluoride and borate. Another type of luminescence detectors are optically stimulated luminescence detectors, or we call them OSL. This is a solid-state detector containing aluminum oxide, and similarly, the amount of radiation exposure is measured by stimulating with green light from either a laser or light-emitting diode source, unlike the thermoluminescent detectors, which requires 100 to 300 degrees Celsius for the energy to be released. Similarly, the amount of light released during optical stimulation is directly proportional to the radiation dose and the intensity of stimulation light. So here, luminescence detectors are generally used to measure absorbed or accumulated dose. Now we have quick review. Question number 8. So that's it for our solid-state detectors. Next up, we have the chemical and nuclear changes.